So in this video, let's take some of our colligative properties and use them to find information about each other. Here we've got 100 grams of water and 10 grams of an unknown non-electrolyte that is added, maybe sugar or something. We stir it up, and then we measure its freezing point. We find that it freezes at 1.23 degrees Celsius below zero. If the K of freezing is negative 1.86 degrees Celsius per molal, use this info to find the mole fraction of the unknown, find the molar mass of the unknown, use the Clausius-Capron equation to find the temperature of boiling. You go ahead and assume we're at sea level and that your delta H vaporization for water is 40,700 joules per mole. And also find the temp using our colligative property calculations, Kb of 0.52. Let's do that to compare the two. Go ahead and give these a try, see what you can solve, and then come on back. All right, if you're back, well, let's first start with that mole fraction of unknown. Let's think for a minute. What do we have? I've got a weight of water, a weight of unknown, and a change in temp. So if I have change in temp, then my change in temp is going to be equal to some K, in this case F, because we're freezing, times the molality, which we know is negative 1.86 degrees Celsius per molal. And then, well, I need the moles over the kilograms of solvent, which I do know the kilograms of solvent, it's 0.1. I don't know the moles, but luckily I do know the temp change, minus 1.23 degrees Celsius. I can actually use the change in freezing point to solve how many moles those 10 grams represented. I know the weight of water, so I can also find the moles of the weight of water, because what is our mole fraction of unknown? It's mole of unknown over mole total. So I can get the moles of water from the weight. I can get the moles of the unknown from its freezing point change effect. I can add them to get the moles total. Water, 100 grams, it's 18.016 grams in 1 mole, so it's about 5.55 mole of water. As to our mole of unknown, well, times by 0.1, divide by negative 1.86. What's that going to come out to be? Mole of the unknown, oh, my negatives will cancel, 0.06613. So I have my mole of unknown, I have my mole of water, which means 0.06613 divided by 5.55 plus 0.06613. 0.0118. So about 1.2%, which, well, it makes up about 9% of the total weight of these two combined. It probably weighs a lot more than water does. In fact, let's figure that out. Let's find that molecular mass. How do we do that? Well, I have the weights of the unknown, then I have the moles of the unknown. Molecular mass is just grams over mole, and I know that it's 10 grams over 0.06613 mole. I could double both, triple both, the ratio would maintain, so the sum multiplier will turn that bottom into 1 mole. Use that same multiplier at the top to get how many grams, or we can just divide these two to do it as well. What we'll find when we divide these two is that it comes out 151.2 grams per mole, which is like 9 times, maybe 8-ish, 8.5 times more than water. And so, yeah, it makes sense that it didn't contribute nearly as much as that 9% of the weight represents, because it's way less than 9% of the particles. So we found our mole fraction of our unknown, and now we have the molar mass of our unknown. And on its own, that's a great problem. There are actually plenty of times that we can use the boiling point change or the freezing point change to help us discover the molar mass of a material, as long as it's reasonably soluble, so that we can have enough of it at those temperatures to see a reasonable change in order to avoid too much air in our calculation, this was actually a very good way to solve molar mass. Other forms were things like osmotic pressure and so on. However, let's continue this down to our temperatures of boiling. Well, we can do our first one fairly easily if we just want to plug it into the equation real quick. Remember, my delta T of boiling is going to be equal to my K of boiling times my molality. We were told 0.52 degrees Celsius per molal, and we know that it's 0.06613 mole over 0.1 kilograms of solvent. We'll find that our delta T of boiling is 0.3438 per 100, 0.3438 degrees Celsius. So it wouldn't raise the temperature of boiling all that much. Let's check it against thinking about this in terms of vapor pressure, though. To boil, if we're at sea level, we need our vapor pressure to be equal to the atmospheric pressure. So what we need is the mixture to have 760 torr vapor pressure. Well, normally that's just at the boiling point, but we have things in solution, so our boiling point is reduced. Our real vapor pressure is going to be equal to the pure vapor pressure times the mole fraction of our solvent. What's our mole fraction of solvent? Well, we know the other was 0.0118, so 1 minus 0.0118. So the total minus the unknown must equal the remainder being water, which means the mole fraction of water is 0.988236. I know what our vapor pressure needs to be. It needs to be 760. There's some pure vapor pressure that when you multiply it by 0.988236 will equal 760. So how hot did we have to get it to be exerting enough vapor pressure that when you remove 1 and 1.2%, it'll just happen to be 760? What is the vapor pressure we needed it to try to exert if it was pure? Because we're going to have to get up to that temp before the reduced vapor pressure is at 760. Well, we can solve that. That ideal pure vapor pressure needs to be 769.054. So we need to know at what temp the pure vapor pressure would be almost 770. Because that's where the reduced vapor pressure is going to match the outside atmospheric pressure. Well, natural log, we'll make this pressure too, so 769.054 over, we'll just use boiling point for our second one. I know two pressures we need to relate. I'm trying to solve the temperature where it's this pressure. Why use 760? Because I know the normal boiling point, and that's always a quick reference. This is going to equal negative 40,700 joules per mole over 8.314 joules per mole Kelvin, 1 over temp 2, and that's what we're actually trying to solve. So I have my pressure that I need the pure vapor to try to exert. What temperature would that be? Because that's going to be the new temperature where I'll reach boiling. Minus from that T1, I could use any pressure and any T1 that I know. I just happen to know the boiling point, 373.15. That is the normal boiling point for pure water. I want to know at what temperature will the normal pure water have 769 torr. Need to divide and rearrange a little bit. 0.011843, when I take the natural log of those, is going to equal negative 4895.36 Kelvin times 1 over temp 2 minus 1 over 373.15. Divide that across to the other side. Negative 2.419312 times 10 to the minus 6 is going to equal 1 over temp 2 minus 1 over 373.15. Let's add that to both sides. 0.00267747 is going to equal 1 over T2, which means T2 is going to be 1 divided by that, or 373.48 Kelvin, which I can turn into Celsius. I can say, hey, subtract 273.15. I find that is 100.33 degrees Celsius, which compared to earlier where we said 0.34. So the two are actually pretty darn in line with each other. We got a little bit of rounding error from various bits in our calculation. We made the assumption of delta H vaporization, despite that we're looking at temperatures over a slight range difference. That introduced only an incredibly small error, which is why these come out pretty dang close to each other. So while we could always calculate out the new boiling point by knowing the mole fractions and using Clausius-Capron equations for any solvent, if somebody has determined the KFs for that solvent, then we can also use the molality to make this approach. So different tools to get to the same answer depending on what information you have available. But all of these are colligative properties, all based on the amount of stuff dissolved and how it affects physical properties like boiling point.